All right, let's look at hypothesis testing and what in the world it is and when to use it. Here is an example. All right, so you have a coin. Coins usually, if you toss them a bunch of times, 50% of the time, you get heads. So say I want a trick coin. I think if I had a trick coin for my whole life, I could trick a lot of people and make a lot of money in different ways, or at least always get my way. So I go to a coin shop and I ask, do you guys have any trick coins? The guy says, sure. Awesome. He gives me the coin to try out. The coin costs $10, so I'm not so sure I want to use it. I try it out. I try it out 300 times. And when I try it out 300 times, 58% of the time, I get heads. Wow. Does that mean it's a trick coin? I'm going to use a hypothesis test to find out. I want to test to see, is it so unlikely that I would get 58%? So this is kind of weird. What I'm going to do is first assume that it's not a trick, that it's status quo. The status quo for all coins is that 50% of the time I get heads. Now I'm going to do an alternative hypothesis. Perhaps for just this coin, it is actually greater than 5% because it's a trick coin. So when I did my test, I got a p-hat equal to 0.58. I want to test now, this hypothesis test, to see how likely is 0.58 to happen. So I want to see, is this significantly small? And what I mean by that is that if I had just a regular coin that has a 50% chance of getting heads, if I toss it 300 times, what's the chance that I get 0.58? Is it a big chance? If it's a big chance, then I'm going to say, okay, whatever, it's not a trick coin, it just kind of randomly happened. If it's super, super small, okay, if it's significantly small, I might have second thoughts. So here's what I'm going to do. First thing I'm going to do is just check my conditions. You guys remember all those conditions for normal curves, n times p is greater than 10, random, greater than 10% of the population. I have to do that because I'm going to use a normal curve. All right, tested my conditions, all's okay. Now I've got to draw my normal curve. My normal curve is going to have that center at 0.5, and once I've figured out this, once I've got my center, I need to figure out my standard deviation. Since this is a sample, I'm going to use standard error, and as you remember, standard error equals this equation. I plug everything in, and I get 0.03. All right. Now I label all of the parts of the normal curve here, and I'm going to actually put in my p-hat. So my p-hat was 0.58, and I'm going to shade in the region over here, because this is the probability, or my p-value, the probability that I actually get 58% or more when I'm using a regular coin. So to find this value, I'm going to use my normal CDF. All right, so I'll use that normal CDF, and when I use my normal CDF, I end up with a p-value of 0.0038 or 3.8%. This means that if I have a normal coin, there is a 3.8% chance of getting 58% of heads. So a normal coin, this only happens 3.8% of the time. Now, is that significantly small? Is that so small that when it happens, I think it's so unlikely to happen that this must not be a real coin? This must be a trick coin. So how do we decide what significantly small is? Well, we call that in statistics alpha. And alpha is the rate that I think is significantly small. It will vary by situation, but typically we say 5%. I think anything smaller than 5%, I just wouldn't really see it happen. And if I did, I'm so surprised that I'm going to question the situation. I'm going to question whether it is a real coin. So in this case, 3.8 is less than 5%. So I am going to say this is not a real coin. Since 3.8 is smaller than 0.5, than the 5%, 0.05, I'm going to reject my null hypothesis. And I'm going to look at this instead, that p is greater than 0.5. So I have rejected the null, and I am now going to assume this alternative hypothesis that p is greater than 0.5. I do have a trick coin, and I'm going to spend the $10 and go ahead and buy it.